Section 6.2 deals with differential equations, and in our course we're really going to, well, at least for now, we're really going to focus on a specific type of differential equation that ends up being an exponential growth and decay problem. So there's two things that we can do with differential equations, and we've talked in 6.1 a little bit about visualizing them using slope fields. And the other thing that we can do for at least certain types of differential equations is find a general or particular solution using integration. All right. So in this first example, we're gonna do both. So the first example here, we have this differential equation, dy dx equals x squared over x squared times y, and we're asked to sketch a solution of the differential equation which passes through this point. So as we know, when we do an antiderivative or we do an indefinite integral, we get a constant of integration, an unknown constant of integration plus c. So what that basically means is, for any given integrand, I could have an infinite number of solutions, all of which will be vertical translations of one another, right? So those are the general solutions. And if we pick one of those to use based on some initial conditions, then that gives us a particular solution. It gives us one option among many different options of what that original function would be. So here's our differential equation. Here's our slope field. And we're asked to draw, sketch a solution through the point 1, 1. So that point is pretty close to there. And if I follow this slope field from there, it looks like I'm going to do something similar to that. And then here we kind of level out, and then we're going to have a horizontal asymptote down there somewhere like that. All right, so that's a particular solution based on a given point and a slope field that's based on this differential equation. All right. Part B, we're going to find the particular solution by integrating. So let's look at the process we use there. If you look at this differential equation, it has x's and y's. The first thing that we really want to do is separate the variables so that we work it this way. We have 1 over y dy equals x squared dx. So I've multiplied this dx over here, and I've divided the y over here, so I get it in this form. And then what I'm going to do is integrate both sides. All right. When I do that, integrate 1 over y dy, I get ln of absolute value of y. When I integrate x squared, I get x cubed over 3, and I have the constant of integration. The very next step, after, as soon as the integral symbol and the dx and the dy disappear, I should have a plus c here on the right. All right. One thing that's true is in both cases we get a plus c. I get a plus c over here and I get a plus c over here, and I've kind of swallowed those up all in one constant of integration. So from here I want to solve for y. So I have the natural log of y. I'm going to exponentiate both sides. So when I do e to the ln of y, I just get y. I do e to this side is x cubed plus 3, I'm sorry, x cubed over 3 plus c. And just as an aside, the way I went from this step to this step is really that this part here is e to the x cubed over 3 times e to the c. I'm sorry, it's e to the c. Right. This is just some other constant that I've renamed here c sub 1. All right. This right here is the general solution. So I haven't solved for that c, and whatever c value I choose will just make a vertical translation of this graph, of this y. All right, so I need to find this c value, and to do that I'm going to plug in my initial conditions, x equals 1, y equals 1, that I was given in that point. So I plug those in and I can solve for c. And I get 1 over e to the 1/3. All right. I plug that 1 over e to the 1/3 back in for this c sub 1. and I simplify it, I get e to the x cubed minus 1 over 3. This is my particular solution.